Okay, so we'll start the session on machine learning for science, a refresher from Ahmed Kachkach, who's a software engineer at Google. Ahmed, the floor is yours.
Thanks. Welcome, everyone. So we'll do just a very light refresher session, where we'll try to just remind you of some basic machine learning concepts before we get into more advanced things. And hopefully we'll have some maybe 5-10 minutes for questions and go into more advanced topics if you want. So since this workshop is about AI applied to science, we're going to try to first talk about how so far science has used data and statistical methods. So if we go back to maybe like earlier times, so as a scientist, you would run some experiments, you make some observations, and you're trying to basically reconcile this with our model of the world. So say you're analyzing planets and you're trying to understand how gravity works. You try to come up with some kind of mathematical model which predicts what you're observing, and usually you have some variable in there, some g, let's say, and you're trying to figure out what this value is, and you look at your observations and compute the value of this variable. So this, in a way, is already some kind of machine learning. But of course, things get more and more complex. And so now the typical data-driven approach, let's say, to conducting scientific experiments is you have some hypothesis they're trying to prove or disprove. So you design an experiment, you go, you collect all your data with some instruments or on the field. And from after you've collected your data, you're going to try to model this. So this might be just computing simple statistical measures like means of some variables or something, or much more advanced computations that we will see. And once you have your model, usually you will gain some understanding of the world or advanced science. And this is spoken like someone that has nothing to do with science. That's why maybe this doesn't seem that familiar. So let's take a somewhat practical example. So let's assume you're sent to Mars to analyze how to grow plants on Mars. And you find that some parts of Mars are very fertile, but others are barren, and you're trying to understand why that is. What do? You go and you collect measurements. You try to find the levels of various minerals in the soil, and you try to correlate that with the yield of the soil, the fertility. So you plot your data, and it looks like this. So first you have a hypothesis. You think it's phosphorus that makes the soil more fertile, and it seems to be the case. Great. But what can we do with this data? These are just raw observations. We cannot really use this to predict if a new piece of soil is going to be fertile. So we need to build some kind of model. So that's where optimization comes into place. So what we mean here is that we have all our data on one side, and we have a simple model of how we think let's say phosphorus and soil yield are related. We're going to talk about the particular model we mentioned here. And then we need to define a loss function. So a loss function, in simple terms, is how wrong our model is, basically how inaccurate it is at predicting what we're observing. And so the optimization process is selecting which variables, like which model best matches our observations. In very simple terms, there's some nuances here because we usually have some training data on one side, but we want to check that our model actually learns something that generalizes, doesn't just memorize individual data points. So usually you will optimize over your training data, but you will evaluate over a separate set of data points. And so to make it more concrete, So one optimization procedure that is very popular is stochastic gradient descent. And this will come back, I'm sure, in future talks that we have during the workshop. So to give you a refresher on how this works, when we perform stochastic gradient descent, we will iterate over our data in batches. So a batch is a small group of data points. So let's imagine you have 1 billion data points. You're not going to take all 1 billion at once. You will go maybe 64 by 64 data points. Every time we will compute predictions given our current model, and we will compare these to what we want to predict. So that's basically computing the loss function. And we will use this loss to update our model to be a little bit more correct gradually. And as you see, like in this simplified diagram, so maybe this is where we start. This is our initial model. It's very wrong. And gradually, we will usually go step by step until we reach some kind of minimum. And this is the simplest use case, which usually never exists. It's never like this. You usually have some complex loss function, and you get stuck in some local minima. But just for the sake of the argument, this is how it would work in a convex case. And here, this is a very simple example of like running stochastic gradient descent. We have a batch of inputs. We compute predictions. We compare them to our labels. So we get an error or a loss. And so we get like an error per data point. And then we would compute some kind of simple loss based on this data. And we use that to update the model. And specifically, when we say update the model, like the most common approach is backpropagation. So specifically in the types of models we'll talk about today. So in this algorithm, basically, we make one forward pass to make the predictions, compute the loss, and we use this loss to then update our model in a way that makes it slightly less wrong on our batch. And again, it's this gradual process iteratively over many, many, many batches that ultimately leads us to find the right model that matches our observations. And so the model that you should be all familiar with, the simplest one, is linear regression. So this is basically when you take observation and you just put the line that makes the most sense through your data points. And in this model, we have two variables that we're trying to find, the weight and the bias. So in our simple example where we have only one variable, that would be like a weight W and a bias B. And we're going to do the process that we already described to try to find the right values for W and for B. In this case, though, you can observe that we match the data here in the middle, but maybe not so much on these extremes. Does anyone have any idea what would be a better model for this data, other than linear regression? Any ideas, any suggestions? Yeah, something like that. So what we could do is we just take our model. So now instead of assuming that they're linked linearly, we can assume that it's a polynomial relation. And so what that means is we just add one more variable to our model. Now it's W1 and W2. Can you still hear me? I think the microphone turned off now.
Can we try speaking?
Test. I think it's off. The light was on, yeah. I can just be loud. I'm just not sure for the stream. Like, are they gonna hear me if I just speak on? Very weird. It just turned off all of a sudden. Okay. So like I said, our model wasn't expressive enough to match our data. So what we can do is just make our model a little bit more complex. So we add one more variable and we make it a polynomial relation. And voila, we get a very good match for our data. Of course, here we're skipping over many nuances. So as an example, I could have made my model, like I could have added 1 billion more variables, and then we would have an even better fit, except that it wouldn't generalize to new data points. So that's why what we really care about is not performance over our training data, our loss function over the training set. We care about performance over a separate validation set. And there, to make that work, we usually have to do things like regularization and all of that, which we will not get into today. Okay, this works good. And so things from here keep getting more and more complicated. So is this too loud? Or no? Good. So in this case, we had one variable, one thing to predict, very easy. What happens when we have several variables? What happens when we have 3 variables? What happens when we have 5,000 variables? Also, there's many other problematic cases like categorical variables. How do we treat those? How do we handle data that is very sparse, or like very sparse in one specific part of the input space? Maybe we want our model to be robust to some things, like if I multiply all my inputs by 10, I want my model to have the same prediction. So there's all these nuances that depend on the problem. And so very quickly, something as simple as a linear regression no longer gets the job done. And so people started coming up with more and more ways to model the world, I guess. So one of them is, say, a decision tree. This is one of many machine learning models. It's a model where at every junction of the tree, you make a decision. is this variable lower than this? Is this equal to that? I'll go left or right. Then people were like, why use one decision tree when you can have 1 million decision trees? So then we had random forests, which is what we call like ensemble methods, where you take many simple models, put them together to get one more advanced model. And there were many other approaches. Support vector machines was all the rage at one point. Everyone was using SVMs for everything. Now, not so popular. And then there was deep learning. And so I would say this, I don't remember exactly, but maybe 2012, 2014, suddenly all these methods that people have been working on for decades became very practical to use and started solving many problems much better than any other model available. And we'll try to understand why that is. And so the basic principle of deep learning is that we have a series of matrix multiplications with a nonlinear function in between. And this is how we model the relation between our inputs and our outputs. So it sounds very simple. You've probably seen like diagrams like this before. But from these basic principles, we can build a lot of different models that do a lot of different things and perform incredibly well at most challenges we have. So to show it in code, this would be equivalent to taking your inputs, applying every time a nonlinear function, plus make it multiplying again by, as we've seen in the linear regression case, by weight of bias, and then computing some kind of loss, and using an optimizer to decrease this loss. And of course, here I'm keeping things very simple. No DNN looks this simple nowadays. You always add some weird things like batch normalization here and there, and you have to pick some obscure optimizer that works well on your architecture and stuff like that. So yeah, like I say here, DNNs are not a model. It's more like a series of concepts that we use to build models. And based on your choices, you can get very different outcomes. So you can have totally different architectures. We're going to see some later. You can have different ways to even train the models. That you don't need to follow the SGD example I gave. Say like in reinforcement learning, things look very different. Or now there's like this diffusion models where they're trained in a very specific way by gradually adding noise to the input. Yeah, so it's like a huge field. It's more than just one model. It's an entire discipline in itself. And one advantage of DNNs is that they scale really well with more data for various reasons that we'll get into. Other methods at one point, as we collect more and more data, would just have about the same performance. But DNNs seem to always continuously get better. Now it's getting to a ridiculous extent with large language models, which here this is on a log scale, and you can see every year pretty much the size have been multiplied by 10. Another thing that these models are really good at is representation learning. So in simple terms, what we mean by representation learning is that with DNNs, we don't have to massage the inputs and make them look a specific way. So this was particularly the case with images. So back in the time, if you wanted to build a computer vision model, you would say download OpenCV, run all these filters that you downloaded from some Stack Overflow thread. You would, I don't know, compute edges on the image, compute all shapes, run KNN clustering on top, and do all this magic, and then feed that to a simple model. But the thing is, these operations were heuristic and not learned end-to-end, so a lot was lost in this process. And with DNNs, given that they're very expressive, you're able to actually learn how to process raw inputs and the output. And so this is useful for images, this is useful for natural language, for sound, video, all these high-dimensional inputs, but also just when you have very high-dimensional categorical variables, that's also a very useful characteristic of DNNs. And one of the ways we represent inputs in DNNs is as embeddings. And I think this is like one of the most powerful concepts that we have. One reason why this is, oh, this is working. No, it's true. Okay. So yeah, one of the reasons why, yeah. Good. All right. We had 0 microphones, now we have 3 microphones, so that's great. So yeah, one of the reasons why embeddings are particularly powerful is that they basically allow you to represent discrete values and they are only updated when you see a specific example of that value. So say if you have like a simple model like linear regression, you update all the weights that you have every time on every single data point. So it's hard to learn, memorize things that are very specific to one input. And embeddings allow you to do this, so you can scale to much larger data sets. And we'll see this in the next talk. And so one last thing we will talk about is how we can model more complex relationships between our inputs and outputs, and specifically sequences or interdependencies between data points, basically. So as you know, in the real world, things are all interdependent. So if you go back to our example on Mars, if you have one piece of soil that is fertile, well, the one next to it might also is more likely to be fertile. But initially we assumed that they're all independent and there's no relation. And this is the assumption that we've been making most of the time, mostly because it's hard to model these dependencies. And these dependencies are everywhere. So if you have chronological data, what happens in the future, of course, depends on what happened before. If you have natural language, words are, of course, interdependent in a sentence. In images, if you have an image with a dog, well, you're, of course, more likely to have another dog than have a spaceship or a meal. And social graphs and recommender systems, and in all these fields, we always find the same pattern where the data points are not actually sampled independently from a space, but they're interconnected. And so how would people model this before? In the simplest case, you would use something like a Markov model, which is a very simple probability of moving from one state to the other. This breaks immediately as you start modeling anything serious. Like it works mostly on toy examples. There's like other methods like hidden Markov models, which work slightly better, but again, they're a little bit too simplistic. For forecasting time series, we had very simple models, linear models like ARIMA, like autoregressive approaches. Again, these work well in a very simple case where you have one variable, but if you have to deal with categorical variables and 12 time series, then it breaks immediately. And so with the advent of deep learning, people started using more complex approaches like RNNs. So for example, LSTM is something you might have heard of. Again, without getting into details, these approaches didn't always succeed. And for images, convolutional neural networks are worked for a while and are still used nowadays. They were also used for sequential data and audio synthesis. But these approaches struggled with a series of problems. The biggest one probably is that they didn't work that well on very long sequences and couldn't learn long-term dependencies. So if, say, you see one word and then 10,000 words later, you see a word that is related to that one, these models would really struggle with these approaches because they would basically go through the data one time step at a time, or like a number of time steps at a time for CNNs. And also, they were particularly slow to train and run inference on, again, because they really, in the architecture of the model, you had to do things sequentially instead of looking at all the inputs at once. And this is where attention is all you need comes in, and I'm going to leave that for the next speaker. Yeah, I think that's going to be all for this talk. Maybe we can take some questions from here. So it was very superficial, high-level overview. So if you have any questions, we can also talk about more advanced things. Hussein, how much time do we have? Okay.
Thank you for answering the questions. I think everybody can hear me even without speaking in the mic. So a very nice and clear presentation. I just have an interesting question, I think. Can we learn without optimizing any loss function? Like, because everything is like formalized in the paradigm of loss optimization, find the loss. And like the first person on earth who thought about that. I mean, like they formalize it in terms of loss. Can we completely change it? Can we think about the problem differently? Yeah, thank you. Yeah. Any thoughts, comments? I appreciate it.
Starting with the hard questions. I feel a bit underqualified to talk about this. I'm not that good at the optimization side of things. I would say, like in the applied ML side, Yeah, maybe I'll just answer like this. Yeah, in the applied side now, everyone thinks in terms of optimization. So for me,